All right. Ladies and gentlemen, class recording has started. So, last week, we introduced this idea of vectors in two dimensions. We talked about how the concept of a vector doesn't change, but how we define it in two dimensions, a little bit different, right, with the magnitude and the direction and stuff like that. The end result of that being that now that we know how to define a vector in two dimensions, we now have to deal with those vectors in two dimensions because we do things with those vectors, like add them and subtract them and multiply them to get representations of what's going on out there in the real world. So, adding and subtracting vectors starts with the arrangement of those vectors. In order for us to add or subtract a vector, they have to be arranged in a certain way. And we refer to that method as head to tail. So we need to set up our vectors in an arrangement that we refer to as head to tail, which I'll show you here in a second. Okay? Once we have arranged those vectors in the head to tail formation, now we can find what we refer to as the resultant vector, or we sometimes call it the vector sum of those two vectors. The resultant vector, or the vector sum, is generally what we're going for in this situation, and usually a lot of times too, because very rarely do we have only one vector quantity affecting a situation. More often than not, we're going to have to take into account lots of vector quantities, and that means that we have to add all of them together to find the combined effect of all of them. So first we have to arrange vectors in what we refer to as head-to-tail formation. Once we've done that, then we can find ourselves the resultant vector, which represents the sum of those two vectors. All right, good there? So let's do some pictures before we talk about what that means in terms of the context of this chapter. So, here's a map. And it's a map showing, like, let's say the backyard of some kids, right? So back when you were younger, you used to play pirate, right? And you set up, a little treasure map to lead somebody wherever they're starting to the treasure. So, you start your treasure map at the sycamore tree, and you tell whoever's going after the treasure, maybe it's your little brother, right? Take 5 paces north, then take 3 paces east, and that's where the treasure will be. Okay? Although judging by the setup of your backyard, considering that you have a dog, if it's your little brother, perhaps you've just buried some dog poop and he's going to go dig that up. I don't know, but whatever. Whatever works for you. But anyway, we talked about the idea that the distance traveled of this trip would be 8 paces, because you go 5 paces north and 3 paces east. And because distance traveled is a scalar quantity, the direction doesn't matter. But this purple vector represents the displacement from start to finish, right? And displacement being a vector quantity, we're only concerned about where we start and where we finish. And it's not 8 because of the fact that we changed direction, right? This purple vector right here represents the sum of these two vectors, because first thing we did was arrange vectors A and B head to tail. Notice, B starts right where A finishes, and that's the head to tail arrangement that we need in order to add vectors together. So first we line them up correctly. Then the resultant vector is the one that we draw from the beginning of the first one to the end of the last one. And we'll come back to this, so don't worry about writing it down just yet, okay? But the resultant vector, or the sum of those vectors, is represented by the one big vector that we draw from the beginning of the first to the end of the last, okay? If we relate it to something you did in lab, right? Here's a map of Fenwick's hometown of Centerville, right? The first trip that Fenwick took went from home to the newspaper, and then he went from the newspaper to the florist. This purple line represents his displacement during that trip. But his displacement is the sum of these two vectors. Okay? That's great if it's 2, but it works for more than 2, right? Let's say you make your treasure map now a little more challenging, right? 5 paces north, 3 paces east, and then 4 paces southeast. That's fine. You still have to line them up head to tail. So B starts where A finishes, C starts where B finishes, and then you draw in the vector from the beginning of the first one to the end of the last one. So this purple vector, which is now labeled D, these arrows on top just represent that it's a vector quantity, right? The vector D represents the sum of A plus B plus C, okay? But it's not just 5 plus 3 plus 4, right? Doesn't work that way with the vectors. That's why we don't just write D equals A plus B plus C, right? The D is not 12 paces. That would be the distance traveled, but that's not the displacement, right? And then you could do it with as many vectors as you wanted to. Like, here's another, our lab from the other day, right? Fenwick's first 4 legs: newspaper, florist, pharmacy, post office. They're all lined up head to tail. This one starts where the previous one finishes. Same thing here, same thing here. And then the purple, the resultant from where we started from the beginning of the first to the end of the last. Okay? Good there? So, what does this all mean? The key point to this section of your book, come on. The key point to this section of your book, right? You already wrote down the first 2 things. This is the part here at the bottom that's important. It's a key point. How do I know? There's a key next to it. So, right? To add 2 vectors, A and B, place the tail end of B at the head of A. The sum, which is C, is the vector that goes from the tail of A to the head of B. So that's just summarizing what we talked about. First, to add them together, you got to line them up tip to tail or head to tail. Once you've lined them all up head to tail, you draw one big vector from where the first one starts to where the last one ends. And that vector represents the sum of all of those vectors. And we refer to that vector as the resultant vector. So to add 2 vectors, vector A and vector B, place the tail end of B at the head of A, right? Line them up head to tail. And then the sum, vector C, is the vector that goes from the tail of A to the head of B. So from the beginning of the first one to the end of the last one. Good there? Good idea? Okay. When we are talking about displacements, generally they line up head to tail. Because when we talk about like a set of directions or a map or something, you do this step first, you do this step second, you do this step third, you go in sequential order. But there will come times when we don't have these vectors in sequential order. We will be required to rearrange our drawing in a way that allows us to more easily perform the calculations that we've been talking about. So the next thing we want to talk about is the idea. that if we draw a vector, regardless of where we draw it on our picture, as long as it points in the same direction and remains the same length, it's the same vector. For instance, let's say all of these vectors A represent a wind speed, right? Or let's say a wind velocity, because that's a vector quantity, right? So if this wind is blowing at 10 miles per hour to the northeast, we draw a vector like this to represent it. But regardless of where we draw that vector, it still represents 10 miles per hour to the northeast, whether we draw it in this location or this location down here or this location down here. Just because we physically move its location on the drawing, as long as it stays the same length and stays the same direction, it's the same vector. Good there? Why is that important? Well, like I said, when we're dealing with displacements, generally they go in order and it's not a big deal. But a lot of times when we have to deal with things like forces and velocities and stuff like that, the exact order that they go in is not quite obvious. But the important part being, it really doesn't matter. Because if we have this set up like here in the top, you have vector A in red, you have vector B in blue. These vectors are lined up head to tail. They're in the proper arrangement. And then we draw a vector from the beginning of the first to the end of the last one. That vector represents the sum of A plus B. But the bottom picture, instead of going A first and B second, we went B first and A second. What do we find out about the resultant vector there? It's the same. Because addition shouldn't matter what order you do it in. If we're talking about scalar quantities, 3 plus 4 equals 7. The same as 4 plus 3 equals 7. That's true of scalar quantities, but it's also true of vector quantities. It shouldn't matter what order we draw them in. As long as we have them arranged properly, we should get the same resultant vector. And we find out that that is the case. That regardless of whether you do A plus B or B plus A, you should get the same thing. And I have no idea. I did all of these the same way in PowerPoint, and I have no idea why these arrows are like 4 different lengths right here. Like I did them all exactly the same way, but apparently that's not how it shows up here. So if somebody's up there nitpicking, because I know some of you are like, why are all those arrows the wrong direction or the wrong length? Somebody's thinking that. I know. All right, good there? So what does that mean? Well, we have to find this resultant vector. That's generally what we're looking at, the sum of these vectors. Because like I said at the beginning, there are many times when we have several vectors that are influencing a situation, we need to find the total result of all of them. So how do we do that? Okay? Oh, sorry. Fenwick's ride right here. 3 legs, resultant vector. While this wouldn't be the most efficient use of his time, if he goes to those 3 places but in a different order, right? As long as he starts at home and ends at the pharmacy, it doesn't matter what order he goes in, the resultant should be exactly the same. Although these 3 vectors that I drew are not the same 3 vectors as these 3 vectors, okay? But if I arrange these 3 in a different way, we should end up in the same spot. Okay? Do you trust me on that, or do you want me to show you?
Trust.
Oh, thanks, Paul. Appreciate that. All right. So in the lab that you guys did on Wednesday, you figured out a way to measure this resultant, or in the case of this resultant. How did you measure that vector? What did you do to find out its magnitude? You used the little ruler thing, right? Okay, and you measured the length of that vector, and it came out to be whatever, 12.7 miles or whatever it was, and that was great. Okay, But that only works in certain instances. When we do that graphically, right, we were allowed to do that on our lab because on that map everything was drawn to scale, right? So if we draw this picture to scale, if A and B are exactly as long as their magnitudes are, representative of their magnitudes, then we can just measure the distance of C and measure the angle, and we would have magnitude and direction. But you don't necessarily have to write this part down. That really depends on how accurate we are with our drawing. But there's a lot of times when we don't have the time or the ability to make that accurate of a drawing. So there has to be a way for us to figure out C without having to draw everything to scale using a protractor and a ruler. And there is. And that's generally what we're going to do most of the time, okay, using components. So I'm going to show you this picture first, then we'll come back and write this down. Okay? So here is that same A and B that we looked at in the previous picture. But as you can see here, what they did was they took A, this vector here, right? And A has its own set of components. It has an x component and a y component, like this. And then B, which is drawn right here, has its own set of components as well. It has an x component and a y component. Okay? If these are both on the x-axis, what do you think we're probably going to do with them? You did this in your lab the other day. What do you do with all the x-axis components? Add them together. Let's see if this works. All right. If I take this, or not, let's see if this works. Keep. If I take this and move it down here, and I take this and move it down here, what do you see about the two of those put together? They make the length of that side, right? It's the total of the x components. And then if I take this one here and move it to this spot, and I take this one here and move it to this spot here, right? It makes the total y components. Now, why is that important? Because ultimately we're looking for this vector C, right? By breaking everything up into its components, we have now made C the hypotenuse of one big right triangle. Do we know the two sides of that right triangle? Because we just add up these, which we know, and add up these, which we know, and now we have a big right triangle where we know the two sides. If we know the two sides of a big right triangle, how are we going to find the hypotenuse? Pythagorean theorem. How are we going to find the angle? Trig functions, right? SOHCAHTOA, right? Okay? So even though we ended up with two vectors that didn't make us a right triangle, originally, by breaking them up into their components, we end up with a big right triangle. And now we know how to handle that. Okay? So, to summarize, right? Nope. Okay? The most precise way to add vectors is by using components. So the first thing you do, find the components of all the vectors that you're trying to add up. In the case of the picture we just looked at, that would be A and B. So you break A up into its components, and you break B up into its components. Once you've done that, add all the x's together. And that gets you one big x component. Do the same thing for the y's. Add all the y's together. And now you have one big y component. And if you've got one big x component and one big y component, what do you know about the x-axis and the y-axis? What angle do they form with each other? 90 degrees. And now you've got the legs of one big right triangle, which you can use Pythagorean theorem and trig functions to find all the other parts of that right triangle. Good there? Okay. Please don't write the rest of this down. I just want to show you this real quick, okay? This is all from your book. So, if we go here, on page 123 of your book, there's this picture, figure 4.13. And it says vector A has a magnitude of 5 meters and a direction 60 degrees above the x-axis. So that's the red vector. This is supposed to represent 5 meters. There's my 60 degrees. Okay? Vector B has a magnitude of 4 meters at a direction of 20 degrees above the x-axis. Now, to add these vectors together, I got to line them up head to tail. So now B isn't on the x-axis anymore. But remember, if it's 20 degrees above the x-axis, it's also 20 degrees above any line parallel to the x-axis. So we've lined up B and A properly, and we can then assume this angle is 20 degrees. If you're drawing this by hand, are you going to make sure that this is 20 degrees? Is it going to be 20 degrees if you're just sketching the picture? No. It might be pretty tough to make that happen, right? And it also says that A is 5 meters and B is 4 meters. Maybe I'm just being picky here, but, and maybe I'm just trying to make a point for this problem, it doesn't look to me that B is 4/5 of A. It just doesn't. It looks like it's shorter than that to me. Okay? So this picture might not be drawn to scale, but we still have to find the resultant displacement, or the resultant vector. So, just like we discussed, and please, as I said, don't write this down. This is on page 124 of your book, so if you want to make a note of that. So the first thing they did was break up A into its components by using the trig functions, right? So there's A, and it's got a component here, and it's got a component here. And now we know how big those components are. And then they did the same thing to B. Here's B, and here's this component, and here's this component. And now we know how big those two components are. So the next thing they did was add the x's together. And when you add the x's together, that gets you this side right here. And then they added the y's together. And when you add the y's together, that gets you this side right here. Now that you've got the two sides of a big right triangle where C, the purple one, is the hypotenuse, now you can use Pythagorean theorem to find the length of that side, right? And you can use your tangent function to find the angle. Okay? Good there? All right. Next week we will definitely practice this more and more and more. For the weekend, just a couple of things I wanted you to look at. Page 121 through 126, that is section 4.2 of your book, so it just goes over the stuff we talked about. And then these 5 problems, these are all conceptual problems. They relate to the ideas that we talked about, lining things up head to tail, drawing the resultant vector, etc., etc. But hopefully we'll have those things down so that when on Wednesday, when we come back, we can get into practicing the vector addition and subtraction. Okay? Good there? All right.
How much time do we have left?
12 minutes?
Can I take the quiz roll?
Sure.